All right, it's Wakefield here, and we're going to be doing some online labs to try to do our best to, do two things. We have two goals. Two goals at CCU. CCU. Right? Number one, no Rona. Right? So, our goal is to not have you all get the Rona and not have me get the Rona. Because, you're young and, you'll get the Rona and you'll spread it to a bunch of people, but you probably won't die. I'm old. I might die. So, goal one is no Rona. Goal two is that you learn some stuff, right? So, we're doing these online labs to accomplish these two goals. You can't get the Rona if you're at home, and you can still learn while not getting the Rona. So, throughout the semester, we're going to hit you with some online lectures, and this is the first one, and this is going to be really geared towards doing a review of basic calculations that you learned in Gen Chem that you're going to need in organic chemistry. All right, so the basic calculations we're going to look at percent composition, percent recovery, percent yield, some basic density stuff, and then a retention factor, which is one that you haven't learned before, but you'll use later on in Organic 1 and Organic 2 lab. So I'm going to put this disclaimer out there now. I'm an organic chemist. I don't really get hung up on sig figs. Right, as long as you don't go super duper crazy with your numbers, it's fine. So things might not look 100% sig figgy, but they don't really need to in organic as much as, let's say, Gen Chem or quantitative analysis. So just keep that in mind. Don't get too heated or stressed out about sig figs, because I'm not going to. So first up is going to be percent composition. And this is basically how you figure out how much of a part of a mixture makes up the entire mixture. So that mixture can be 3 solids that you've separated, and you figured out how much each one weighs, so now you know the percent composition of that mixture. It could also be something like a molecule, where you know all the atoms in the molecule, and you can figure out how much by weight each of those atoms contributes to the overall mass of that molecule, right? The formula is super basic, right? It's just the mass of the part that you're looking at, the thing that you want to know what percentage it is, divided by the mass of the whole mixture. Let that mixture again be a physical mixture you can see, or an atom, times 100%, right? So for this, we're going to start out by looking at how you do percent composition for a molecule, and then we'll do percent composition of a mixture. So for a molecule, right, you have to figure out the mass of each element in the molecule. That is the, oh God, what did I do? All right, cool. What you're going to get this semester is you're going to get a lot of videos of old people fumbling around with technology, and you guys are all going to laugh. It's going to be great. So, we'll just leave that in. Leave that in for the people. All right. So first we need to figure out the molecular weight of this guy. That's going to be the total. So the molecular weight of methamphetamine is going to be our total mass, right? It's going to be the bottom of our equation. And then the mass of each element is going to be the mass of the part, the thing on top. All right, so we've got our formula C10H15N, Right, to get the mass of each element, you need to take the atomic weight times the number of atoms. Right, so let's go do some math. Right, so we look at carbon. Carbon has a molecular weight of 12. Now, is it really 12.01 yada yada? Sure, but we're just going to, do this pretty easy here. So we're going to say it's 12 times 10. It's going to be 120. Hydrogen has a mass of 1. We've got 15 of those puppies, so that's going to be 15. And then nitrogen is 14. We got 1 of those, that's 14. So these are all of our parts. We can add these up real quick. Get 149. Now these would all be atomic mass units, atomic mass units, atomic mass units, atomic mass units, right? Your percent composition is going to be a unitless number, because what you're always going to be dividing is you're going to be dividing two numbers that share units. So those units are always going to cancel out. So here, if we do percent comp of carbon, so how much of the mass of methamphetamine is carbon, it's going to be 120 AMUs divided by 149 AMUs times 100%. That's going to be 80.5%. Right, we can do percent composition of hydrogen in this molecule. It's going to be 15 divided by 149 times 100. Again, let me be better about my units. Times 100%. That's going to be basically 10%. And then we're going to do percent comp of nitrogen. Right, I don't know why that one got a line and the other ones didn't. Let's fix that. Bam. All right, nitrogen weighed 14 AMUs divided by 149 AMUs times 100. Right, so that's going to be 9.4%. Now, I rounded some stuff real quick to get like nicer numbers. Notice how I wasn't super stressed out about going like 9.39597%. Yeah, we don't care that much, right? Now, if I add all these up, I should get 100% or really, really close. So I have 9.4 and 10 is 19.4. Oops, too far. Plus 80.5. That gets me to 99.9%. So there's a little bit of some rounding error there, but close enough for organic work. So that's how you do percent composition of an atom, which you've probably seen before in Gen Chem. Now we're going to do it of a mixture. This is something that you have to do in the very first lab of Organic 1. Now, so all you have to do for percent composition of a mixture is you take whatever mass of the component that you want to know the percent composition of and divide it by the total mass of the, what's it called? I'm really good at this. Of the mixture, right? So you take the part, divide it by the whole. Super easy. So, I'm going to give you a story throughout this, right? So you've seen the structure of meth. You know its percent composition, right? You had a lot of time watching Netflix, right? And you were like, oh man, Breaking Bad. This seems like a how-to. All right, let's do this, right? But you hadn't made it all the way through organic, so you're just making some trash meth at your house, right? And so you know your meth's not great, and you need to like kind of cut it to stretch it a little bit further because you're not making enough. So you add some lithium metal and red phosphorus. Two things that sound awful, but are actually things they put in meth to cut it, to like stretch it, right? So you have 5 grams of your horrible Gen Chem grade meth, and there's only 1 gram of actual meth in it. There's 2.5 grams of red phosphorus and 1.5 grams of lithium metal. Now, hopefully you're thinking this math is really easy. right? I did that on purpose so I didn't have to pause every 3 seconds to use my calculator. So let's look at this real quick. So what's the percent composition of actual methamphetamine in your meth? Well, you have 1 gram of meth. You have 5 grams of mixture of overall solid. Multiply that times 100. It's going to be 20% of your horrible Gen Chem grade meth is actually meth. So not great. What is our percent composition of lithium? Well, how much lithium was in our mixture? So we have 1.5 grams of lithium metal. So it's going to be 1.5 grams divided by 5 grams times 100. 30% lithium. Right, and the last one is red phosphorus. Oops. Writing on my iPad, if I touch the screen at all, it stops writing, right? So red phosphorus, percent composition, it's going to be 2.5 grams divided by 5 grams times 100%. Is going to be 50%. Right, so again, we can add all these up and check ourselves. 50 plus 20 plus 30 is 100%. Oh, great. This is also a little take home that don't do meth, because stuff might just be all not meth. All right, so that's how we do percent composition. When you have to do it in the lab, you're going to be given, you're going to isolate solids. And then you're going to have to weigh those solids, figure out their masses, and then use that to figure out the percent composition of your mixture. We're going to talk about percent recovery. And this is where you look at how much you got back when you do typically a recrystallization, right? You start out with a certain amount of impure material. At the end of your recrystallization, you get pure material, and you want to know how much of that impure material came back as pure. Right, so again, you're normally going to see this as as something you do in a recrystallization. So our formula here, right, is going to be the mass of the collected solid divided by the initial mass of the solid, right? So, again, you're still making meth. Breaking Bad seemed good, but you got busted. And you didn't call Sal, so you were going away, right? So, let's say that we started out with 200 grams of your awful Gen Chem grade meth, right? And then they got 38 grams of pure meth from that 200 grams. What is the percent recovery of this recrystallization that they did? All right, so that's just going to be what we started with, right? So our starting mass, is 200 grams, right? Our recovered mass is going to be 38 grams. So this is just 38 grams divided by 200 grams times 100. It's going to be 19%. So they recovered 19% of the mass they started with. So this might actually be worse than the meth we thought we had before, where it was that's about right. You said your horrible Gen Chem meth was 20% meth, and they recovered 19% meth, and 81% of the stuff went away. That's pretty good. They did a pretty good job, right? So when you're doing a percent recovery, you just need to take what you got pure after the recrystallization, divide it by the mass of the impure stuff you started with, and multiply that by 100. Super straightforward. So next up is percent yield, and this is the thing that you're going to use most often in organic. Almost every reaction that you run, you want to calculate the percent yield because that lets you know how well the reaction worked, right? In organic chemistry, you're really concerned about two things. Did I make the thing I wanted to make? And did I make a lot of it, right? Was my reaction, did my reaction work well? And did I get the right thing? And the percent yield is the answer to did my reaction work well, right? So this is measuring how efficient your reaction is, how much of your starting material gets converted to your product. And the formula for this is super straightforward. You got bludgeon with this and Gen Chem, I'm sure, right? It's the actual yield that you got divided by the theoretical yield. So it's what your yield was divided by how much you could have ever possibly got from this reaction. If the reaction was perfect, what would that number be, right? So you typically, one of the first things you need to do is you need to figure out the stoichiometry of the reaction, right? So how many moles of starting material are needed to make the product, right? So you need to know what that ratio is. And so before we get too far into how you calculate theoretical and actual yield, I want to take a look at stoichiometry. So whenever I talk about stoichiometry or gets talked about in Gen Chem, right, we always kind of use some sort of like real world physical example. And I'm going to use the low-grade prison or, I don't know, college freshman cheese sandwich, right? That is 2 pieces of white bread and 1 piece of cheese, right? So if you think about making a cheese sandwich, it takes 2 pieces of bread, 1 piece of cheese, and you get this high-quality sandwich, right? So your ratio is 2 breads, 1 cheese, gives you a sandwich. So if you have 4 pieces of bread and 2 pieces of cheese, you can make 2 sandwiches. If you have 4 pieces of bread and 3 pieces of cheese, you can still only make 2 sandwiches, right? Because bread is your limiting reagent, right? You have to use all your bread in pairs, right? So you get that kind of in your head where you're like, okay, I need 2 of this molecule and 1 of this molecule to make my product. If I double the amount of my one reagent and don't change the other, I'm not going to be able to use all of that excess reagent, right? So if I have 4 breads and only 1 cheese, I still only get 1 sandwich and I have bread in excess. Right, so that's kind of your first example where it's like, hey, you have 2 pieces of bread and a piece of cheese, and you make a sandwich, right? Then they're like, okay, we're not going to show you, the 2 pieces of bread and the 1 piece of cheese. We're just going to put the number 2 in front of the bread. So it's like, hey, you have 2 breads. You have 1 cheese. You get a sandwich. And that's how you kind of do it through Gen Chem, right? Where, you are doing simple reactions where you're like, okay, H2O plus O2 equals H2O, and you balance the equation, and you're like, okay, cool, I need 2 of these to make, to make 2 of these. So it's a 2 to 1 to 2 ratio of your molecules, right? So you have the numbers in front. Organic, we kind of meet you somewhere in the middle, where for almost every organic reaction that is written out, you never get that number, the coefficient, in front of the parts of your reaction. What we rely on you to do in organic is we rely on you to look at your starting materials, look at your product, and say, okay, looking at this picture of my product, there are 2 breads and 1 cheese. And it's a little hard to see. Trust me, there's 1 cheese in there. Right, there's 2 breads and a cheese. So that must mean my ratio is 2 breads to 1 cheese make a sandwich. All right, make my product. In this case, my product is a sandwich. Right, so one of the things you have to be able to do when you're doing organic is you have to be able to look at the reaction, and even if you don't know what the reaction is doing, it's incumbent upon you to find pieces of the starting material and pieces of the starting materials in the product to figure out how many starting materials you needed to make your product. So let's go over. All right, so if you're in Organic 1 right now, you're right at the beginning, and these are just crazy lines. Fine. But if you were able to ever do as a kid, those like pictures in the Saturday morning paper where it was two pictures, like which things are different, and you had to look, and you're like, oh, his tie was striped, but over here his tie is polka dotted. If you could do that, you can do this, right? So we look at this reaction, this first one here, we'll put it in green. This is all gobbledygook, right? Means absolutely nothing to you. Fine. But you can recognize patterns, right? This right here, right? That is right here, right? So there's one of this thing with this aromatic ring, which is this ring right here. There's one of those in the product. And there's one nitrogen in the product, right? So looking at the picture of starting materials to products, you can see that it's a 1 to 1 to 1 ratio. So it takes 1 mole of the ketone and 1 mole of the amine to make the product. So there's a 1 to 1 to 1 ratio. So when you're doing your theoretical yield calculation, you know what the mole to mole ratio is for when you fill out when you do your equation. Now down here in this next example, again, this reaction, gobbledygook, means nothing to you, right? But again, we can kind of tie ourselves to this ring, right? So this ring, there's actually 2 of them. There's one here, and there's one here, right? And then this ketone here, there's just that guy right there. So you have 2 of this ring to 1 of this makes 1 product. So you have a 1 to 1 ratio of ketone to product, but you have a 2 to 1 ratio of aromatic ring to product. So when you're doing your theoretical yield, when you're looking at the aldehyde, okay, so the thing with the ring, right, that you need 2 of those for every 1 product that you want to make, right? So even though we don't give you the coefficients out in front of the molecules 95% of the time, just being able to look at the pictures gives you enough information to be able to do those mole-to-mole ratios. So, like I said, your theoretical yield is the maximum amount of product you can make, given a certain amount of starting material. And you need to calculate your theoretical yield for 2 things. First, the theoretical yield is what you need to calculate your actual percent yield. But second, the theoretical yield has you figure out what your limiting reagent is, right? So if you have a reaction that has 2 components, you figure out the theoretical yield for each of them, and that lets you know which one is the limiting reagent. Whichever one has the lowest theoretical yield, that is the reagent that is limiting how much you can make in this reaction. Now, we went through stoichiometry and looking for mole-to-mole ratios. This right here is where you put the mole-to-mole ratio, right? So here at the beginning, you take the mass of whatever starting material you're trying to figure out the theoretical yield for, and you take its mass, and then you convert it into moles. So at this point, you have moles. You cancel those moles out with however many moles of starting material that you need to make 1 mole of product, right? And then you have a 1-to-1, and then you have your moles of product is what you get out of the green box. Then you multiply the moles of product by the molecular weight of the product, and that's going to give you your theoretical yield. So if we look at the reaction we just had, right? So if we have this and this making this. Oh no, hopefully you can see the end there, right? So we know that it's a 2:1 ratio, right? So if we were looking to do the theoretical yield of this aldehyde, in the green box, it'd be 1 mole of product, right? And 2 moles of the aldehyde starting material, right? So that's where you put in the number you get from looking at the reaction and figuring out what your mole-to-mole ratio is. So that's where that's important. So let's do one. I think the one I have is pretty simple, but it'll give you a good idea of how to do this. All right. So again, I'm really setting up these word problems. These are way better than you got in like junior high and high school, where like Timmy was selling candy bars, right? Boo. No, we're slinging some stuff here. All right. So the man busted you, but you broke out of jail because Shawshank is a how-to on how to break out of prison. And you watched that thing like 4 times on during quarantine, right? So you get out and you're like, you know what? No more Gen Chem grade meth. We're making that glass stuff, that good stuff. And you want to have a good yield, right? So you're going to start out with 2.4 grams. Oh, I didn't mean to move it. We're going to start out with 2.4 grams of phenylacetone, which is this compound here. We're going to have 0.5 grams of methylamine, which is this. And that's going to make 2.1 grams of that good stuff, right? Now, because I didn't want to have to worry about like the stoichiometry for this, I'm just telling you it's in excess. You have way more of that than you need. So the only things you have to worry about for being your limiting reagent is going to be phenylacetone or methylamine. So let's calculate our theoretical yield. All right, so first, we have to get the molecular weight of phenylacetone. Right, so quick counting here. C, 1, 2, 3, 4, 5, 6, 7, 8, 9. C9, H5, 8, 10, O. So quick math. We're going to pause this. I shouldn't have said anything. We just thought I was a wizard. So this is 134 grams per mole. Sweet. So if we look at our previous little equation, right? There we go. I need my mass of my starting material, and then I need the molecular weight. So my mass of phenylacetone is 2.4 grams. So we're going to say 2.4 grams, right? And there's going to be 134 grams in every 1 mole of phenylacetone, right? If we look at our ratio, I have 1 phenylacetone to every methamphetamine that I make. So I have 1 mole of meth for every 1 mole of the starting material, right? And then 1 mole of meth has a molecular weight of 149 grams per mole, right? And that is going to get us to the theoretical yield in grams. And that is going to be 2.67 grams of meth. Small batch, right? I mean, you're a drug kingpin, but you got to start out small. Make sure you got your cook up right. All right, now we can do the same thing for our methylamine, right? Methylamine, we have 0.75 grams of methylamine. We can figure out the molecular weight real quick. So we have 0.75 grams of methylamine, right? We need 1 mole of methylamine. 1 mole of the amine goes to 1 mole of meth. We know meth weighs 149 for 1 mole. Right, so we got to figure out our molecular weight. This is CH5N. So this should be 34 grams per mole. So this is going to be 34 grams. There we go. Do some math. After mathing in my head, clearly, I get 3.29 grams of meth. So if I start with 0.75 grams of methylamine, I make 3.29 grams of meth. Right? If I start with 2.4 grams of phenylacetone, I make 2.67 grams of meth. Since 2.67 is less than 3.2, the phenylacetone is my limiting reagent. And as a result, this is my theoretical yield. Right? So whatever theoretical yield is lower is your limiting reagent. Now you have the number that goes in the bottom for your yield calculation, right? Because percent yield, again, is actual yield over theoretical yield times 100%, right? So our actual yield, let's click back, was 2.1 grams. So 2.1 grams. Our theoretical yield is 2.67. And we get 79%. Okay, now, if you did the math along with me, your calculator said 78.6516, blah, blah, and you fell asleep, right? We typically don't use percentages in our yields in organic, right? Organic is very practical in that sense because, honestly, there's not a huge difference between 78.65% and 79%. So we have a tendency to round yields to the highest to the nearest whole number. So do this. This is good. Bad. Right? So don't give a bunch of decimal points in your yields. Make sure that you keep them to the nearest whole number for organic. If you go on to quant or instrumental with Budner and Simpson, if they saw this, they would have a stroke. But in organic, we stroke out over 4 decimal points on our yields. Right? So, and again, remember what the very first slide said? I don't do sig figs. So, I know there's some sig figgy issues here, but this is the yield. Right? So, just make sure you get your yields to the nearest whole number on the yield, and we'll be good. Right? So, there is yield. Next, we're going to talk about density. Now, you might be rolling your eyes super hard at the thought of doing density again after Gen Chem, but you'd be surprised at the number of people who get density dunked on and just can't do it, right? Or kind of stress out when they have to. So when this comes up the most is in a procedure, I will specifically know something is a liquid and I will give you a mass because I want you to have to actually do the calculation to actually kind of like flex that muscle that is like dormant in your brain from Gen Chem. Right? So you have to remember the formula, right? Density is going to be your mass, typically in grams, divided by a volume, typically in milliliters, is how we do it in organic. Almost every density you're going to see is going to be, grams per ml is going to be the units, right? So in this scenario, you've decided to go straight. You've left your life of crime behind no more meth for you. You're going to take these chemistry skills you've developed and you've gone straight and you're a scientist person. Ooh, scientist people, right? And you need to are working in a place where you have to use triethylamine, and you need to use 2.3 grams of triethylamine, and triethylamine's liquid. So you can't just go to the scale and like scoop it out, right? That's way too difficult. But you can just figure out what volume you need, and the density of triethylamine is 0.727 grams per ml. I picked triethylamine because I'm a big loser and I remember its density from 15 years ago. So yeah, oops. Okay, so our density is going to be change it here. It's going to be so many dots, 0.727 grams per ml. We need, 2.3 grams? 2.3 grams. And we need to figure out our volume, right? So we need to figure out basically X, right? Here we're going to hit them with some algebra, right? Multiply both sides by X, right? Boom. You get 0.272 grams per ml times X equals 2.3 grams. Divide both sides by 2.7 grams per ml. Divided by 0.27 grams per ml. When you do this, right, you can think about this as like multiplying by the inverse. So it's going to look like this. ml 0.272 grams. That's going to allow your grams to cancel. You'll be left with equals X, right? Let's your grams cancel. This gives you your mLs, and that'll be, you're in a 3.17, sorry, 16 mLs. Something to remember, right? If your density is less than 1, you always need more mLs than you have grams. If your density is greater than 1, you always have less mLs than you do grams. So if you keep that in your head, that will help you figure out if your answer kind of makes sense logically. You can be like, oh wait, I have a density that's less than 1, but my milliliters came out to be less than the number of grams. Okay, that can't be right. Right? So just keep that in your head. Density less than 1 means more mLs. Density more than 1 means less mLs than grams. The other thing that you're going to use density for pretty frequently in organic is if you have mils of a substance and then you want to know how many grams that is so that you can calculate your percent yield, your theoretical yield, so you can get your percent yield, figure out limiting reagents, things like that. So, all right, you thought you were gonna go straight and narrow, but you're coming to work and there's some morphine just fell off the pallet in the shipping area, and you're like, oh man, this is easy money. A little acetic anhydride, boom, heroin. One last score, then I'm out of the game for good. And so you figure out you got 330 mils of acetic anhydride, and you need to know how many grams that is. And you have the density, which is 1.8 grams per ml. So let's do this. So again, density equals grams per, in this case, ml. Your density is 1.08 grams per ml, right? You don't have the grams, but you have the milliliters, right? 330, make sure I did that right, 330, good job me. So you're going to multiply both sides by 330. Bam, cancel that out. 330 on this side, mLs. So then that's going to be 300, and numbers are hard, 356.4 grams is going to equal X. Right, so that's the other thing you're going to do a lot of times is you might see in a procedure add 15 mLs of something, and then you realize that you need to calculate the mole so you can figure out limiting reagent, so you're going to have to figure out the grams really quick. So it's pretty straightforward. No, I did skip like molarity, right? So like big M equals moles per liter. It's the same thing, right? It's like an amount in a volume. It's the same thing as density. You can do your density calculations. You can do your molarity calculations. Again, this is all stuff you crushed in Gen Chem. That's how you got here. All right, so no big deal there. So the last thing here is something new. This is retention factor, and it gets abbreviated RF. So you're just almost always going to hear it referred to as RF, right? In this, the RF is the distance a compound travels on a TLC plate, a thin layer chromatography plate, divided by the total distance the solvent traveled. So RF is a property that's going to be constant across TLCs that you run. So if you have a compound that has an RF of 0.4 in a certain solvent, no matter how big your TLC plate is, that RF is always going to stay 0.4 if your solvent stays the same. So you can run different reactions and know, hey, this compound's 0.4, and no matter how long your TLC plate is, when you make that TLC plate, RF is going to stay 0.4. Or you can do an experiment and your RF of a given compound is 0.4, and then 3 years from now, another student can do it with a totally different TLC plate, a different size, but if they use the same solvent, they're going to get 0.4 for their RF. Right, so this gives you a way to compare a compound to basically itself, to basically know, hey, I have this value, and this is a way for me to check to see if it's the compound that I want, right? So the formula is super simple. The RF is the distance the compound traveled in centimeters, typically in centimeters, and then the distance the solvent traveled in centimeters. So the setup for these, you're going to do a whole lab on this, but I just want to give you a quick rundown. Right, you have like a beaker or TLC chamber. And you have a plate, and you have solvent in it. We'll do solvent first. You've got some solvent, and you have a plate that you put in there. Right, here's your TLC plate. And through capillary action, your solvent will move up the TLC plate. And let's say you have on here, you've got your origin. Let me get a different color here. Purple feels good. Right? And you put your compound, you have your compound on your origin, you put it in the solvent, and the solvent starts to move up. And as the solvent moves up, it will carry that spot up the TLC plate. And so that spot will go from being at the origin, and eventually it will move from the origin, which is the blue line, up the TLC plate. Right? And then you'll mark, hey, my solvent moved up to this level, right? And the spot where the solvent moves to is called the solvent front. So you've got your origin down here. You've got your solvent front up here. And then you have your spot here, which is purple. So I have this drawn a little bit nicer on a slide. All right, so you can see here, you've got your solvent front. Here, this is how far the solvent moves up the TLC plate. You've got your origin, which is this is where you start measuring from, right? This is where you put your compounds, where you spot your compounds before you put the TLC plate in the solvent. And that's where you start measuring from. So the height you measure that the solvent traveled is from the origin up to the solvent front. The height you measure for how far the compounds traveled is from the origin up to that spot. All right. So in our example here where we're turning morphine into heroin, morphine is going to be more polar than heroin, and more polar compounds on TLC plates don't move as far up the TLC plate, so they are lower, and heroin would be higher. So if you look at this, this would be probably morphine, and this would be heroin. All right. So let's get some actual numbers in here so we can kind of do our RF calculations. So here we have some numbers in here for you. So if you were doing this in the lab, you would be able to see your spots, and you would take a ruler and measure from the origin, which you marked beforehand, to the middle of your compound spot. And you do that for each compound. Right? And then you would measure from the origin to the solvent front. So you have to mark the solvent front when you're done doing your TLC plate. So I made the math super easy here. So the RF for this first compound, right, would be the RF would equal 3.5 centimeters divided by 10 centimeters. So the RF is going to be I made the math really easy, still goobered it up. It's going to be 0.35, right? RF is a unitless number because both numbers are in centimeters. Those cancel, so you're just left with a unitless number. For our blue thing, the RF is going to be 6.5 centimeters divided by 10 centimeters, and that's going to be 0.65 for our RF for that other compound. So this is really easy. As long as you measure correctly, you're going to just do a simple division of your compound, the height of the compound, divided by the height of the solvent front. And that's it. So I hope that this quick lecture was a good refresher on some Gen Chem calculations that you know. This video is going to be up the whole semester, so if we get to a lab and you're like, oh yeah, we went over that, please come back and refer to this, right? I'm going to have a worksheet that all the different instructors should be giving out for you to practice some of these skills. It'll just be more problems, maybe a little bit more in depth, kind of pulling things together. But basically that'll be the lab we'll be working through that calculations worksheet. And just to remind you, I know I used a lot of drug examples, and as Mr. Mackey would say, drugs are bad, okay? So don't do drugs. Don't make drugs. Drugs are bad. All right, take it easy.